This is very strange. We're detecting background noise from my microphone.
Oh, Professor, we can see you now.
Okay. Yeah, but the screen stopped sharing, and that's very strange. Okay. All right. Yeah, and now like the chat box is empty for me. This has never happened to me before. Let me try sharing the OneNote again. Okay. Can somebody? Okay, we can see OneNote, and now I can see the chat. Yeah, everything that was written there before just cleared. Very weird. Okay, let's hope that there's no more technical issues like that. Okay. Any other questions about the homework or anything else that we've covered?
Professor, in regards back to question 4, is this something that we should just like discuss like after class or?
If it's a question besides what we were just talking about, I'll go back and I'll reward credit. So I've saw 2 iterations of this, which was either numbers 1, 2, 3, 4, 5, whatever, like this. So if I took off points for that, I guess I'll reward them for.
Yeah, Professor, it's not
Whatever, I
like
don't
to
care.
down. It's definitely not that like that downplaying like your teachings and all. Like we're not like it wasn't intended to stray away from. It was just like
Oh,
from a couple of us who have taken data structures. It was just we just seen the question objectively saying like binary tree, and we just took the formal definition of that and applied whatever we needed to for that question. So that was
yeah,
just
so
like
I'm interested in that because, yeah, I don't know if that's. Anyway, I think does it. Yeah, I don't know what sense having a binary tree would mean without this constraint on it. To me, that's not a binary tree. That's some other type of data structure.
yeah, I think I guess in that class it was essentially just intended for representing traversals, or at least like what you were talking about with like level order traversals. So when you were trying to explain like, or when you were explaining how a tree is stored in an array and just going level by level, row by row,
Mhm.
it wasn't necessarily like something that had to be like the objectively like the tree didn't have to be ordered. It was just to communicate the fact that we were just going level by level when storing the array. So in like that case, as it's written 1, 2, 3, 4, 5, 6, 7, it was
Mhm.
just to show or communicate that that is what a level order tree traversal looks like.
Okay. Yeah. Um, well, actually, now that's something a little different. This level by level traversal, that would be a breadth, something like a breadth first search, where you start at one layer and then or you start somewhere. In this case, it would be, I guess, starting from the root, and then you go to all of the neighbors that connect to that node and look for things there, and um, then you go to their neighbors, and the search sort of expands outwardly. In the case of a tree, that looks like starting at the root and then visiting the entire layer before moving on to the next layer. And yeah, but again, I don't. That's something you can do on a tree. Yeah, maybe this is pedantic. We could discuss this more after class.
Okay, sounds good.
Okay.
Thank
Yeah.
you,
Yep.
Professor.
Sure.
I appreciate it.
Uh-huh. All right. Um, would I upload standard answers for the homework? Yeah, I can upload standard answers. Yeah, no problem. How about the practice questions that I gave. Any questions about that for the midterm?
Hi, Professor. So I'm still a little confused about hash tables, and I know you covered it last class. So I was I guess this is two things. One thing is like I wasn't able to find the video on the YouTube link or the YouTube playlist, so I wasn't able to like find the answer on my own. And the second like actual material question would just be like, when should hash-based indexing be avoided?
Oh, okay, yeah, good. So I'm happy to go over the hash stuff again. I know we kind of went through it quickly last time. The really, that wasn't uploaded to YouTube. The
I
last
wasn't
class.
able to find it, so like it might have been a me problem.
Well, I can double check. Yeah, the other section, the recording didn't compile, so yeah, I had to give, let's see, 10/6/20. This would have been 10/15. Okay, I'll look it up after to make sure that that it's uploaded for everybody if it's not already. Okay. Right. So hash. When do you avoid using a hash function or a hash table? Is when you want to do a range query. When you want to say return all of the results in this range. So that could be, I don't know, data set on household incomes, and I say I want all of the records that correspond to people earning under $200,000 a year, all of those records. So that's a range from 0 up to 200,000, and a B plus tree is going to be the way to do that because it naturally supports searching within a range, where a hash table does not do that. A hash can only return one record at a time. So if you want one record, then you can use a hash. But if you want multiple records returned, a hash isn't going to work. The reason why you would ever use a hash instead of a B plus tree, because it seems like a B plus tree can do everything and more than a hash. But a B plus tree only works if there's a natural ordering to the data, where you can say that this comes before that. If your data is of the kind where you can't order it, like I said, if you're, I don't know, if the index is an emoji, then there's no way to, order emojis. That they're pictures. So which ones come before or after? There's no natural order. So then that's the case when it makes sense to use a hash. Can you go over when to use? The midterm will be released tomorrow. Probably. Yeah, probably after the session tomorrow, because if I release it before the session tomorrow, then I feel like those students will have maybe an advantage. Or no, actually, you guys might have an advantage, because then, while I'm teaching tomorrow's class, you would have time that they wouldn't to be working on the final or on the midterm. And then also, they will have seen the midterm and might have questions that. So I'll release it tomorrow afternoon around 2 p.m. The class ends tomorrow at 1:20. So yeah, 1:30, 2 p.m., something like that. I'll release it, and then it'll be due Wednesday at 11:59 p.m. you should have plenty of time to work on it. I feel like I lost my train of thought. Let's see here. Yes, when to use pointers and when not to. So, basically, I mean, the easy answer is just use pointers, because they work, and even when you might, even in the cases when you might be wasting some space, like if you're dealing with a balanced tree can get encoded very efficiently layer by layer. So if you're very short on space and you're dealing with a balance, something that you know is going to be balanced and remain balanced, you can avoid pointers. Because the leaves will have null pointers. Where if you're encoding it layer by layer, there's no wasted space. I think, let me see if I can find, I think I actually gave a concrete example of this at some point. Yeah, here. So, there's some scenarios where encoding layer by layer can save a little bit of space. That's not a incredibly common preference for people to use, just because pointers are easy enough, and you can prove that the amount of space is no worse than 2 times the amount of what it would otherwise be if you were using a layer by layer method. And that's in the worst case. In the worst case, you're using up twice as much space. But there's lots and lots and lots of other cases where you're going to be saving space. And, you know, like B plus trees, B trees, all of these are built using pointers, not this layer by layer method, for some of these reasons. It makes it easier to save space on a wider variety of trees. So in the case of encoding, I think that this is your question, in the case of encoding a binary tree, when do you prefer the method with pointers versus the method like the level by level or layer by layer method? And the short answer is, if it's a balanced tree, the layer by layer method will save a little bit of space. So there might be a preference there. In all other cases, prefer pointers. Does that answer your question? You also go over the benefit of storing an index file that is separate from the file of records. Yeah, so the benefit is that the file of records, that's this gigantic pile of data. It's a lot of data, and you're not going to be able to access all of it at once. You have to, if you wanted to go through all of it, you'd have to load it in parts. You know, take this part, load it into RAM, look for whatever. If you didn't find it, take the next part of the file, load it into memory, and you know, it's a lot of reading from the disk. And that's bad news. Like, you don't want to read from the disk more than you have to, because reading from a disk is very, very slow. Yeah, it can store a lot of data, but it's very, very slow to access data here. So here you're measuring things in the number of disk accesses, because that's the real bottleneck. I mean, this is no joke, a million times slower whenever you need to access the disk versus accessing something in memory. So if you store an index file separately, then the only thing that the index file contains are keys and pointers, and that's it. And nothing else about the record. So the index file, therefore, can be made very small, small enough to fit into memory. So you have one disk access to load the index file from the disk, put it into RAM, and now you have the entire data structure in RAM. And that's very fast, and now you can find out exactly where the records are that you care about, and then you can do the disk access to get only those records. So that's the reason why. It does take up a little bit more space, but the benefit is that you can load it into memory by itself. And so the performance gains that you get make it very, very worthwhile. Next one, separate from the file of records. Yeah, so I see two students asking that same question. Yeah, does that answer your questions for those of you who asked it? Hash-based indexing is just a hash function to generate a hash table. Feature compared with hash-based index. Yeah, let me go. I'll take these in order. Hash-based indexing is, yes, using a hash function that generates a hash table. That hash table is called a hash-based index. So here, an index is a file, and it's a data structure that's saved in a file. And so that data structure, you can call it a hash table. You can also call it a hash-based index file. They're all the same thing. So yeah, if you have a hash-based index, that's referring to a file which is storing the data structure of a hash table. The hash function is what you use to generate the hash values.
Professor, I have a clarification on that.
Huh?
So when you did that example with like the John versus Johnny, and then those values were like 683 for blah 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 versus like 241110890.
Yep.
And those positions, like the table itself with the SID, the names, the address, the phone numbers, that whole thing was the hash table, right?
No, this thing,
Yeah.
that is not a hash table. This is a hash table, and this is called the file of records. So the file of records, that's the gigantic thing of data. The hash table is an index file. In this case, the index file is a hash table, not a B plus tree. Yeah. So the file of records is all of the data.
Okay, so what is that to the like that pointer? What is that like? Does that say something specifically? Like John, like in the index file, it says John, and then it says something in the. I'm assuming that's the pointers.
Yeah. These are so this is key, and this is actually a block pointer.
Is that
So it
any
points
different?
to the block on disk that stores the record.
Like assuming there are no collisions, wouldn't it just point to a single record?
Not exactly. I mean, if we're being very specific about it, then it would not be pointing to a specific record. It would be pointing to a block that contains the record. And because when you're accessing the disk, the smallest unit on a disk is a block. Even if the record takes up maybe half the block, you don't just get returned half of the block. You're going to get an entire block, no matter what. So, it's really a block pointer. And then once you receive the block, then you do a linear search through it. But the blocks are
Okay.
small.
Okay, thank you. So the hash is the function that generates like the 683400128.
Yep.
And those are index positions in the hash table.
Yes.
Okay, great. And those index positions refer to a key and a pointer, and that pointer refers to the block in the actual record table.
Yep.
Okay, great. Thank you.
Yeah. Okay, so I see another question here. Can I explain question 4E, a B tree compared with a hash-based index? So really, this is just kind of like a linear search versus binary search kind of thing, where you have a choice when you have a bunch of data, and then you're inserting all of this data into a database. Then you have a choice of how you're going to index your data, and you'll be given, for example, two options. Do you want to do a B plus index or a hash-based index? So the point is knowing when to choose what. So a B plus tree. This can do range queries. Again, a range query is when you're not wanting just a single record returned, you want a bunch of records, all of the records that fall within some range. So records of household incomes that are $200,000 or less, or all students whose name ends, whose name begins with the letter J. All of those students, I want them. That is called a range query, and you can only do that in a B plus tree. So for hash-based indexing, this can not do range queries. So really, the basically the default, I think, should be a B plus tree. If you can do a B plus tree, use a B plus tree. But a hash can index keys that have no natural order, where a B tree requires keys to have an ordering. Okay, so numbers, some numbers are smaller than other numbers, so there's an order. to them. It's a natural order. Some come before others. Letters of the alphabet. There's an order. Some letters come at the beginning of the alphabet, other letters come at the end of the alphabet. And so there's a clear ordering to them. And that's required in a B plus tree because you need to decide to break left or break right, or you need to know how to traverse the tree. And so you're doing a comparison. Am I less than or equal to? Like, where do I fall in a range? So there has to be an ordering. But for things like, there's lots of different types of data. Maybe if it's, locations, for example. If it were, you want to index by, city name or by GPS location, then if it's location based, then it's hard to talk about an order to that. So a hash-based index might work well. Like you give a GPS coordinate, and we'll return the record that corresponds to it. Or if you're using something like an image, or I was going to say Chinese script, but I guess that even those characters have an ordering to them. Okay. What are collisions? A collision is when a hash function returns the same value for two different entries. So here, these two records, that's a collision. So John and Amy, if you give John to the hash function, it returns this number, 683400128. If you give the hash function a different name, Amy, then you get the same number, 683400128. That's a collision. These are unavoidable. Like there's going to be lots of collisions. But the hope is these are called collision-resistant hash functions, which means that collisions should happen infrequently, particularly for the things that you care about. So, going back up here and looking at this idea of all possible combinations of letters, 100 long, is a huge set. I mean, A, all A's, up to A, B, C, all of them going up to Z. I mean, any possible combination, I guess including a white space, if you like. So that's a gigantic set. Most you'll never see. Like, there's no expectation that in the real world that you'll actually be encountering any of these. So for the things, these are all possible names, this whole set. But much smaller are, I'll just say, the real names. The names that you would actually encounter. And that's a much, much smaller, inside of the set of all possible combinations of letters. Actual names is like a little tiny piece of that. So long that those things don't collide very often, then the hash function is a good one. A good one meaning it's collision resistant. Collisions don't happen too often on the data that you care about.
Professor, I have a clarification on that.
Mhm.
So previously, like in our last class, we said that collisions were like if you had multiple Johns, and so those Johns would point to a table of Johns. Are those like two? Is that like another type of collision, or is that the same
Yeah.
collision?
So yeah, technically that's another type of collision. Yeah.
Okay. So
Yeah.
in this case, where we have Amy also referring to the same number in our actual index table at position 6, 8, whatever it is, would we see John and would we see Amy, or would we see two of like the same
Yeah.
location?
So the way that it would work is or one way is that the index file here would actually be um, uh, something called a linked list. So, I mean, I'm making some of these things simpler because, well, it's an undergraduate class, right? I mean, like we can't get too deep. But what's okay? So what it actually looks like is here's an index table, and you have the key, and here's a pointer, and this pointer isn't a pointer to a block. It's a pointer to well, it's a pointer to a block that stores a linked list. So it would be, it would point here, and then there would be John and his record, and then that would have a pointer to the next one, who's maybe Amy, and then maybe there's another John, and so really this is a pointer to a linked list. And then once you have the linked list, then you do a linear search. And which one do you want to return? Maybe you return all of them that correspond to that number. And stranger names like, well, not stranger names necessarily, but yeah, some of these will just be a single location. I don't know, Rob, and others will be a chain like this. So
Okay, and so what's in the actual key then? Is it John or is it just a placeholder?
the key here would still be so I'm sorry, the key would be the hash value. So this would
Okay.
be whatever that number is. So where do you go in this file? First, you do the hash, and now you can do maybe like a binary search or something here and go to where that number is, and then follow the pointers into the linked list. And
Okay.
yeah.
Awesome. And one more clarification on the previous point. So when like the function or the hash John gives us the 683400128. So that's referring to the actual position in this index table, the key where you circled the hash, but it doesn't refer to the position of John or Amy in the actual table of records, right?
No, that would be another pointer here. This would be the pointer to the record pointer. So each of these would have a record pointer. So this is actually kind of a multi-layered thing. It's not just the hash index table by itself. It's actually kind of a combination of things. And I mean, these are really good questions. But yeah, they're a little bit. Well, yeah, I'm happy to kind of give hand wavy answers. But yeah, so really, it's a hash table. The hash is both. It can be both the position in a table, if you like. If you can allocate sort of space, and then if you keep your hash function such that any numbers that it produces is within this range, then the hash number tells you exactly where in this list to find it. That's one way of doing it. You don't have to. It could also be like a tree, basically. And so once you get the hash number, then you do a search through the tree to find this record or this location in the index table. That has a pointer that brings you somewhere else that has another data structure that's a linked list. And this linked list would have the key and a few pointers. One is a record pointer, another is a pointer to the next entry. Here, John pointing to Amy, that's another pointer.
Okay, great, thank you.
Mm-hmm. Yeah. Yeah, I appreciate the question. Stuff like that is not going to be on the midterm, but very good questions. Oh, when should hash-based indexing be avoided? When you need to do range queries. Yeah. Hashing can't do range queries. That's when you avoid it.
And one more thing, the hash itself is just the function that gives us this seemingly random permanent number, but it also creates an index table, like when you run the function.
No, so this is why it's called hash-based indexing. The index table is not produced by the hash function. The hash function is just giving you, as you say, a seemingly random number or a pseudo-random number.
Okay.
And then how to store those numbers inside of an index table is kind of another question of how do you get to a particular location in the index table given this hash value. Again, I'm being a little hand-wavy. This is why it's called hash-based indexing, because it uses a hash, but the way that you're actually storing the table or the index table or finding a particular location in the index table, that's kind of a separate process that I'm not going to get into detail with. But yeah, actually, I think you probably already know enough from this course where you could come up with a reasonable scheme of how that would go.
Okay, great, thank you.
Sure. Yeah. Also, if you want in this book, this book has chapters on B+ trees, hash indexes, and it will go into a little bit more detail about that type of stuff. But for the purposes of this class, I'm happy with you guys knowing, use B+ trees for range queries and why, and when would you choose a hash-based index, which is basically when you're dealing with keys that don't have a natural ordering to them. Can I explain 4b? Okay, so I have to pull up the questions here. Here you go, review questions. 4b, be able to explain why you need to have multiple indexing schemes if you want to search through a database based on different keys. Yeah. So, think. Actually, here, I think maybe the other section I made something is better. Yeah. Okay. So this is something that I made for the other class, and these aren't B plus trees. I mean, in reality, they would be something more like a B plus tree, but just to convey the concept, I'm just using binary trees. So here. On the right, that table is the table of records, and that's this gigantic amount of data. So then you can have a separate file, an index table, and that index table is itself a data structure with pointers. Yeah, so there would be children pointers and also pointers for records. Now, if I wanted to find a student quickly based on their student ID, that's a number. And so the tree on the lower left, that is a valid binary tree to return a student based on their student ID. But if I wanted to search for a student sometimes by student ID and other times by name, I cannot use a single data structure. There is no single data structure that can allow you to search efficiently. So you just have to double up. If you want to search by student ID, build a tree for student ID. If you want to search by name, you need to build an entirely different tree that you will then use to search by name. And that's it. Right, so this is called multiple indexing schemes. One index table for student IDs, another index table for names. Yeah, and it's just because there's not beyond just my knowledge. I mean, there's no known data structure that allows you to efficiently move through it based on multiple different keys, because the data structure is built around efficiency for one particular type of key. Does that make sense? Okay. Okay. No more questions? Okay. I'm sure you'll all do fine. If you have any last minute questions or anything, you can always send me a message on Canvas or email. That includes questions on the midterm. If you have a question about phrasing or something seems ambiguous or something like that, you can email me, send me a message on Canvas, and I'll respond as quickly as I can. So, okay. Go back to our section. And I'm going to start a new one. This is ER diagrams. So, ER diagrams we're now moving into this. None of this material will be on the midterm, but this is now we're entering the second phase of the course, done with background and foundations, and now we're moving into the theory of databases, particularly queries. Will this lecture be uploaded by tomorrow? Yes, I'll do that. Assuming it's not corrupted. I hope it's not. I hope it's not. Okay. Okay. So let me turn this off really quick. ER diagrams are actually pretty simple. We're not going to spend a lot of time on them. I'll kind of quickly go over some stuff today, and the next class, we should be able to finish ER diagrams and then move on to the beginnings of relational algebra. And that is, things are going to get a little hairy at particular points there. But right now, this is something easy, ER diagrams. These are entity relationship diagrams. So ER diagram is an entity relationship diagram. Make this bigger. Cool. So these an entity relationship diagram is a picture. It's a picture that you draw. It is not a doodle. It's not like there's. It's not like you're trying to explain a concept and you're drawing something to try to get the point across. This is more like, think of it more like a blueprint, where there's rules that have to be followed. If you're looking at a blueprint, there's important structural components to that picture, and you can't just do whatever you want with it. Let me turn off my camera really quick so I can write more comfortably. Okay. So the point of an entity relationship diagram is to put some constraints on the database. So there's an entity. This is represented by a box. Then there's relationships, and this is represented by a kind of triangle. Oh, another thing that I should say, I'm happy for you to look up ER diagrams and stuff online. I am going to be sticking to the ER diagrams as they are in this textbook. So some of the ways that these drawings look are different if you were to look it up online. For example, so entities connect with other entities via some relationship. So, for example, I don't know, employee has a salary, for example. So entities can only connect to other entities via a relationship. So you cannot connect entities directly together. That's not cool. So entities have to go through relationships. And there's also an idea, let's see. of having a one-to-one relationship or a one-to-many relationship or a many-to-many relationship. In this case, it would be probably a one-to-one relationship. One employee can have one salary. But if you have a manager who, I don't know, oversees employees. Actually, I'll go this way. A manager who oversees employees. Well, one manager can oversee many employees. So that's a one-to-many relationship. It could be the case that one employee can have multiple managers, in which case these would have a many-to-many relationship. One manager can have many employees. One employee could have multiple managers. So there's some that, I don't know, they have like lines along here, stuff like that. If you're looking online, that's not what we're going to be doing. Right. So, yeah, just don't get confused if you're looking things up online and comparing it to this lecture, because we're going off of the notation used in the textbook. So there are a couple of the ways that we're going to be capturing these relationships, be it a one-to-one, many-to-one, is going to be through the thickness of lines, or whether or not these lines have arrows. So there will be a thin line, there will be a thick line, and then there will be lines with arrows. Maybe thick lines with an arrow as well. So in any case, this means unconstrained. Oh, actually, let me put these down. I'll delete that and we'll do a different type of example. I'll get to these soon, the lines. But another shape is an oval, and this is for an attribute. There's some jargon that the book uses about an attribute versus a keyed attribute versus a descriptive attribute, and I don't care at all about any of that jargon. I think it'll be clear enough by example. So let me draw a quick thing here. So let's say we have employees. And employees work in a department. In a department. Okay. So these are two different entities, and each of these will have some attributes. So the employee could have a social security number, a name, and I don't know, a parking lot where they park. Departments can have a department ID, a department name, and a budget for the department, for example. Okay, so these are attributes, and what I want you to start having in your mind is thinking of these as tables. So there will be an employee table, and there's going to be, in this case, 3 columns: the social security number, the name, and the parking lot. Similarly, oh, where'd that go? Okay. Similarly, the department would have its own table. Okay. So each entity is going to be its own table. Okay. Later, we'll talk about tables. When we talk about SQL, everything is table based. So these diagrams do correspond strictly to these types of tables. Now, like, okay, for each entity, there's going to be a key. And now we're going to require the keys to be unique. So here, and we show that as with an attribute by underlining that attribute. So here, the department ID is some unique number for the department, like a social security number is unique for employees. And underlining it is important. That's called a keyed attribute. Whatever, I don't care much about the jargon. But what this shows is that there's going to be, that's going to be your key. When you have an index table, like here, let's see. No, no here. Yeah, so here, this index, what you're indexing on is what's called the key. Okay, so there's many attributes that this table has. In this case, student ID would be a key. Also, we'd have name as a key, not together. But in any case, that's the keyed attribute part of this. Very good. Okay. Okay. So, also, relationships can have attributes as well. So an employee has worked in a department since some time. Attributes for relationships have no keys. Only an attribute for an entity will have a key. All right. Okay, so let me try to move this a little bit. Yeah, just sort of keep in mind. Oh, and then also in the table, you underline the key. Let's see. All right. Yeah, before I give these arrows, I gotta go over this. So 1 to 1, 1 to many, and many to many. Okay. So here I'm going to start talking a little bit about sets, just very quickly. So each of these bubbles represents a set. And this might be the set of employees. Okay, and as a dot here stands for like a record corresponding to one employee. So right now we have 4 employees. I'm just drawing a dot for simplicity. And the departments, this is a department. If it's 1-to-1, that means it's like this. Well, actually, they don't have to go straight, whatever. 1 employee can work in 1 department. That's a 1-to-1. You could not have this, because that would mean that one department has 2 employees. So that's not a 1-to-1. Similarly, you couldn't have this, because this would be saying that a one employee can work in many departments. And here, 1-to-many, this is okay now. This is okay. So 1 can have many. That's what makes it 1-to-many. So employee, department. In this case, 1 employee can work in many departments, but each department can only have 1 employee. This would, I'm sorry, let's see. This would not be okay here, that one. Because a department can only have 1 employee. 1 employee can work in many departments, but okay. And then this is this many-to-many. This also just means unconstrained, is another way of putting it. So here, everything's good. You can have no connections. You can have many connections. That's okay. You can have things with no connections, things with 1 connection. That's okay. All okay. All okay. Because it's many-to-many. You can kind of just do whatever you want. Okay, so that is setting us up for continuing this next class. ER diagrams really aren't that bad. As I said, we'll be finishing it up the next class. So, thanks, guys, and have a good day. Stick around if there's any more questions.